Okay, hello everyone. My name is Dan Cole, and I'm an engineer working with the U.S. Army Research Laboratory up Aberdeen Proving Ground, Maryland. Today I'm going to try to shed some light on the big question, why don't we just 3D print all of it? Okay, so traditional manufacturing versus additive manufacturing. The traditional manufacturing techniques, not all, but typically we'll start with some starting block of material, and we perform some subtractive manufacturing to provide some three-dimensional object, and typically you'll have some waste material. As opposed to the most additive techniques where we start with some precursor material. It might be a powder or some filament, and then using a computer model, we tell some machine where to deposit material point by point, layer by layer, until we have that 3D object. And typically you'll have less waste material with these techniques. So there's a number of advantages of additive manufacturing over traditional techniques. Some of the big ones are the ability to be able to manufacture very complex geometries with very high spatial resolution. So people all across industry and government and academia and even hobbyists are demonstrating additive manufacturing with various types of material systems, polymers and metals and ceramics, biological materials. There are even groups that are now combining some of these material systems into making these multi-material components. So you can imagine there's great interest in the Department of Defense and having this type of capability. We've heard several talks throughout these last couple of days, and trying to get supplies to soldiers. So the ability to actually manufacture something right at the point of need would be a great advantage to the Department of Defense. And so at the Army Research Lab, there's a variety of different projects that are going on tackling some of these basic research problems. This is by no means comprehensive, but just to give a few examples, we have groups that are looking at combining different types of polymers into a given feedstock. Those feedstocks are actually what we're going to feed into the printers and create our 3D objects. So we have multi-material systems there. We have groups that are looking at recyclable materials. There's a lot of waste material that might come off a military installation. Can we repurpose some of that into usable parts? We have groups that are adding nanoscale fillers like nanoparticles and nanotubes to enhance material properties. We even have groups that are looking at optimizing the geometry and mass of materials while balancing things like mechanical properties. So this is really important for aerospace or autonomous systems because typically weight is a premium here. So if we can make these very complex shapes, it would be very difficult with most traditional means. You can even use additive manufacturing to create little keepsakes for your lab. The Army football fans will appreciate this one. So I know our Navy friends would probably want to ask about the last several years, but we're gonna stay in the present and talk about the future. So with all this in mind, we're demonstrating people printing with metals and ceramics and biological materials and keepsakes for our laboratories and offices. People begin to wonder, well, okay, so if we're doing all that stuff, why aren't we just printing everything then? Why aren't we printing airplanes, and why aren't we printing 3D printers? So there's several reasons, but we're going to talk about three big ones today, and I hope that by the end you can get an appreciation for how they're all really interrelated. So the first one is something that material scientists like to refer to as processing structure-property relationships. So this is just really a fancy way of saying that the way in which we start with a material maybe from the manufacturer and we perform some process to it, that in turn provides some structure which goes from all the way from the macro scale to the micro scale down to the nanoscale. So as an example, with polymer materials, the way in which we process a polymer may cause molecular alignment in a given direction, or may provide some internal stresses to the material or introduce some defects. So for an example, with something called fused deposition modeling, where people are printing with thermoplastic materials, you may start with a precursor material that might be pellets that we buy from a manufacturer. And then we have to process this to make it into something usable for a 3D printer, so like making it into a feedstock. So essentially we would heat up these pellets and kind of like a tube of toothpaste, squeeze out and perform this process to get this filament. And then we do our 3D print process, right? And there's lots of different ways in which we can do that. We can print at various speeds, at various temperatures. We can raster in different orientations. All these things result in some final printed specimen. So that printed specimen is going to now have some mechanical properties and electrical properties, thermal properties, and depending on how we actually went through and processed that, that's going to affect those final properties. So all that to say that with additive manufacturing, we don't have a good understanding of many of these techniques yet to really relate those processing structure property. So one thing that we're trying to do at the Army Research Lab is understand some of these multi-scale material properties. So for the example of this printed specimen here, we may perform some tensile tests to look at the mechanical properties. Then we actually start zeroing in using some micro and nanoscale techniques, like the one I have shown here. This is an atomic force microscope map. And so this is several micron, to give some context, you know, human hair is tens of microns. So we're focusing in really on the local scale now. And at each pixel here, we're performing small indentations on the surface that try to get an idea of the relative stiffness and compliance. And what we find is, depending on where we're actually testing that material, we see a different response. And depending on that processing condition, we get a different response. So if we look at, if we look across an interface, for example, so you have our one build connected to the next build, there's some interfacial property there. If we look at sometimes chemical analyses, we'll see that we actually have a different material. So all of this to say that the community needs advancements in these areas to really understand those relationships. So that brings us to our next big thing, which is testing standards. So engineers and designers need testing standards to be able to compare material A to material B and to make sure that these things are safe for use. And you can imagine if this is going to be a safety critical component, there's going to be a tougher standard. And the military has very, very strict standards for parts that might go in something like a helicopter. So with the testing standards, the field has gone so quickly. There's been all this progress made, but the testing standards communities haven't really caught up. So we really need to have rigorous testing standards so that we could be able to compare the same material made by supplier A and supplier B, which then is going to form some feedstock A versus feedstock B. And then eventually we get this printed sample A and B that we may look exactly the same, but perform very differently. And it's really incumbent upon that first set of basic research issues and trying to understand those processing structure property relationships to get us to this point where we can have these rigorous testing standards. Okay, and the last thing that we're going to talk about today is the shifting culture with introducing additive manufacturing more and more into our life. You can imagine that we're going to shift from the situation where we have some manufacturer print a bunch of parts and then store them in some warehouse, and then when we need it, we ask them to ship them to us, versus potentially someday we're just going to purchase a digital license from them and print it right on the spot. So really the people that are going to probably be best designed to bring this into the everyday life are the kids and children that are growing up with 3D printers in their classrooms. And this is an example of an ARL summer intern that was working on a flapping wing micro air vehicle, and many of these parts are printed using that fused deposition modeling technique. So this is really the next big thing I think that will really push this field forward is adopting this culture. And again, this is going to be, there's going to be differences in when you have safety critical components versus ones that if they were to fail, it wouldn't be as big of a deal. So again, to revisit our question, why don't we just 3D print all of it? Well, we talked about these relationships between processing, structure, property. That feeds into having more rigorous testing standards, and then eventually we as a cultural shift and moving from the traditional to the additive side. But if we can do some of those things, if we can control properties across interfaces, that opens up the design space to a lot of really interesting types of material systems where we can actually maybe be printing someday some totally ready to go system that has the structure printed, it prints the motors, actuation schemes, energy storage, maybe even the batteries are being printed right within the structure, sensing and even the logic being printed all at once, and then it's ready to go. So the question, why don't we just 3D print all of it? Well, pretty soon we may be printing a lot more of it than you think, but I think there's lots of reasons, but this is I think 3 big ones that we're concerned with. So thank you for your time, and it was a really pleasure to be here.